Welcome back. So where did we leave off? We have been talking about graphs and we've been talking about breadth first search, and I sketched the algorithm for a breadth first search. And what I want to do is eventually show you the actual implementation of a breadth first search in Python. But to do that, I need another data structure. I need a queue. So we're going to take a little bit of a break from graphs and breadth first search, and we're going to talk about both queues and stacks, which are related data structure. And then once we have that machinery, we'll be able to go back and finish the implementation of breadth first search for a graph. So let me go ahead and define a queue is a data structure that orders data on a FIFO order, first in, first out. So we're going to talk about queues first, and then we'll come back and talk about stacks. So what do I mean by first in, first out? So this is a queue by the normal English definition. You queue up in a line. The first person that shows up in the line is the first person out of the line, not other way around. And that's what a queue is. It's a way of ordering data with a very particular order on how things go in and how things go out of it. So, for example, we can think about a queue as just a list of numbers or letters or strings or whatever it is. But it has there's a special ordering on how things go in and how things come out of it. So for example, if I have a queue, which I'm going to denote as this vertical list here, and let's say so the nomenclature, by the way, we use with queues and stacks is push and pop. So instead of insert and delete, it's push and pop. It's the same idea, it's just that's the nomenclature around queues and stacks. So if I push A onto the queue and then push B onto the queue and then push C onto the queue, then I have a queue with 3 elements in it. A was the first person on the queue, C was the last. So you can think about this as the front of the list, or the queue rather, and this as the back of the queue. Now, here's an important distinction between lists and queues. On a list, I can put things anywhere, right? I can put them in the first position, in the middle position, and the last position. I can delete any element of the list. I can delete A, I can delete C, I can delete whatever. And a queue doesn't work that way. You can push, and you can only push in one place at the end of the line. You can't push you can't cheat. You can't push here, you can't push here, you can't push here. When you push, you notice I'm not saying where to put it in the list or in the queue. I'm just saying push it there, and it's going to go to the very end and do effectively an append. Yeah? And now when I delete, I can't delete C. I can only delete the first person in the queue. So when I delete, I simply say pop. Just delete. And since only one person can be deleted from the queue, the first person that was inserted, the person at the front of the queue or the top of the queue, the A gets popped out, and that's what gets returned to you. Okay? Now, if I push something back on again, I don't say push it into a position. I say just push it. It puts it into the last element. So initially, A, B, C was in the list. In the queue, A popped off. B, C remains in the original position. D gets added now at the very end of the queue. And if I pop, then the B pops off, and then the C pops off, and so on and so forth. Okay? So a queue is a data structure that orders data on a first in, first out. You can only go to one place on the queue at the very end, and only one person can get deleted from it, and that's the person at the front of the list. A stack is also a data structure that orders data, but this is in a philo order, first in, last out. Okay, so let's think what that means. You go to a line to wait in line to get to the grocery store, and the first person in the line is the last one to get out. That is not a line you want to be in. Okay? Now, it turns out stacks are really useful for things like recursion, but we're not going to get into that. But I want to mention stacks, not because we need them for breadth first search, because they're a natural counterpart to queues, and the only difference is this is a philo versus a FIFO. So again, a stack can be thought of as simply as a list. And again, you push things onto a stack, same way. Push A, push B, push C. But now when you pop, if it was a queue, I would pop this A right here because that was the first one in. But when I pop on a stack, the C gets popped out because that was the last one in. Okay? So first in, that's this one here, last out. So think of it as sort of a stack of dishes. I stack dish, 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 and I want to take a dish. I don't reach to the bottom. That would be silly. I grab the top dish. So the first one that was stacked is the last one out, unlike a queue where you would pull from the bottom. Okay, so again, when I pop, I don't specify pop from where. It's pop from the top of the stack. And so now when I push a D on it, A and B have been waiting there, but when I pop, D was the first one in. D was the last one in, so it's the first one out. And then when I pop the B and pop, again, everything empties out. Okay? So that's the queue and the stack. They're basically simple data structure. You can think of it as a list that orders data in a FIFO for a queue and a FILO for a stack. Now, the good news is for you is that stacks and queues are by default implemented in Python. So you don't have to build your own data structure. You could, by the way, and a nice exercise for you to think about is what would it look like? Well, I'd have a list, and a queue would only allow appending to the list, and delete would always remove the first element. A stack is you can only append to the list, and delete is deleting the last element in the list. So you could implement this. You could build a class for a stack or a queue with a push and a pop, and that would be a good exercise. It may take you a little bit of time to do it, but that would be a really good exercise to do it. But here's the good news. You don't have to, because you can import from collections a deque. So DEQU stands for deque, and it implements what is called a double-ended queue, which is simply means that it implements queues and stacks. So let's just go ahead and see what that looks like, because this we're going to really need to implement breadth first search for the graph algorithm. All right, so I'm going to import from collections the deque, and I'm going to initialize a queue. So queue is equal to deque paren paren. This is simply calling a constructor, and now queue is a double-ended queue, which means it can act as either a queue or a stack, and you'll see in a minute how that is. All right, so queue.append. So the push operator in a deque is called append, despite what I said earlier about the nomenclature being push and pop. Deques use the term append. So to push, you push A onto the queue, you push B onto the queue, and what I'm going to show you down here is what my queue looks like. So I pushed A and I pushed B. Now, if this is a queue, then when I pop, A should come off, and if it's a stack, when I pop, B should come off, and I'll show you how we can do both of those with this one data structure. I can, like a list, ask for the length of the queue. So simply the same operator is the len operator, and it of course will return 2 because there are 2 elements in the queue. Now, if I want this to be a queue, and when I pop, I say pop left. So this is the left part. That was the first thing that came in, so it's the first thing that's going to come out. So think about the list as I'm appending, I'm putting it this way. So if I want to stack, I want to pop from the right, and if I want a queue, I want to pop from the left. This, by the way, is not how I would have implemented this. I don't like this mixing of nomenclature, but it's fine. This is the way Python does it. So queue, of course, is the queue. I've appended 2 things on it. So when I pop left, call the function associated with this deque, since this will treat queue as the letter Q, the variable Q, as a queue, and it will remove the first thing and hand it back, print it, of course. So there's the A, and then what's left is a single element. Now, so of course, if I ask for the length of the queue, there's only 1 element left because I had 2 and I popped 1 off. Okay? So let's add something else to the queue. That's C. Now if I pop left, that was the inserted before, so that will come off. And there's my B right there. And of course, I have 1 element left. And if I pop left, then the C will come out. And of course, now my queue is empty. So if I say pop left, it will return, of course, an error because there is nothing left in the queue. Okay? So be careful with the queues, just like a list. You can't delete things that don't exist. You can't write outside of the index. And although I won't show it here, so this is how you use the deque from collections as a queue. Append is push, and pop left is pop. Okay? And that's all we need to know for breadth first search. Now, if you wanted to do this as a stack, instead of pop left, you would just pop right. So you append in the same way, and you pop right because that was the last one in is the first one out. Okay, good. So at this point now, we have everything we need to implement a breadth first search. So we know what a graph is. We know how to represent a graph. We know what the breadth first search algorithm is, and we have this newfound data structure, the queue, which you'll see in a minute. We need to keep track of the breadth first search as we are visiting vertices. So when we come back, we're going to write a little bit of Python code to implement breadth first search. See you in a few minutes.